This is Software Engineering Radio, the podcast for professional developers on the web at se-radio.net. SE Radio is brought to you by the IEEE Computer Society and by IEEE Software Magazine. Online at computer.org/software. SE Radio has an opening for a volunteer host to produce 5 episodes per year. To apply, please follow the instructions on our website at se-radio.net/contact.
Welcome to Software Engineering Radio. I'm your host, Gavin Henry, and today my guest is Tim McNamara. Tim is a well-known Rust educator. He wrote the book Rust in Action and received a Rust Foundation Fellowship 2023 in recognition of his efforts to promote the language. He also runs Accelerant.dev, a consultancy focused on the Rust programming language. Tim hosts a YouTube channel, podcast, and is active on most social media platforms as Tim Click. Tim, welcome back to Software Engineering Radio. We last spoke in 2021. Is there anything I missed in your bio that you'd like to add?
No. Thank you very much for the introduction.
No problem at all. Okay, so today the show is talking about Rust, error handling in Rust. So I really enjoyed your talk for Rust Nation UK, which was about Rust errors. So I thought I'd like to get you on the show again, because it really helped me understand them. So I think it'll be great for our listeners to not only explore errors in software and bugs in general, but how Rust helps us with them to avoid them and give us the flexibility to do what we need to do.
Well, look, it's a pleasure.
So I want to lay the foundation before we move into what you called the 4 levels of errors in Rust, for that talk you did for Rust Nation UK. So let's start. Bit of a high-level one. What is an error?
This is a deceptively difficult question to answer. That's probably why you're starting with it. Because there are almost there are multiple different, right? So if we think of, let's just say that we think of a simple program as starting, going through a series of instructions, and then terminating. An error, we could define it as essentially at one of those steps, some input, it receives something that it does not understand or does not expect. And so, or there is some precondition that isn't satisfied. And then the program cannot continue to the next step. Essentially, you can think of an error as a fork in the control flow, and error handling as being a way to essentially split the program apart, and down the happy path, let's say, or the main path is the control flow that you sort of intended. And down all of these error paths, which also could be used, we could use the term exceptional paths, which kind of hints at the name of exceptions, are smaller, less likely cases, which we have thought about beforehand as programmers, of essentially ways of dealing with problems that we expect that we might encounter. For example, I talked about input, and I meant that in a very general sense. But if you are a web framework, you expect that people will send you all sorts of nonsense from the network. And so your web framework should deal with input that does not satisfy, let's say, HTTP, and the definition essentially of what is valid input and what is invalid input sort of slightly changes at each step. But the other side of what an error might be is something that is completely unexpected, or the program might encounter a state in which it's impossible to continue down any path. And the typical response, most programs at that stage, will be to just crash. The operating system will just kind of close everything down, close all of its files, shut down all of its network sockets, free all the RAM, and essentially ask the user to restart the program. And the way that I think of errors is to think of them as a sort of forks in the road, or from what we intend or expect.
Perfect. And would something like a program, or Rust in particular, assuming that's an input is a certain thing, that could also be covered by what you're saying, where the inputs are wrong, as in dynamically typed languages. You're assuming it's something, but it's not.
Right. We have more inputs than just the data itself. So that every block or every statement or every expression essentially has some extra material, like the data type that it expects. And if you pass a string into a function which is really trying to perform mathematical operations, you're likely to have a very bad time. Perhaps not although there are some languages which have essentially said that our approach is to just accept that and do it the best that we can, irrespective of the input. And so my understanding of Perl, for example, is that if you pass in a string to a function that accepts something numeric and it uses ASCII literals, so essentially you have numerals in the string or at the start of the string, then Perl will just accept that as a number itself. And so there are huge philosophies essentially of software and what is acceptable or permissive in a large spectrum. And that word dynamic is really important because Rust is a very static programming language. It's very fussy about data types. It's easy to laugh at Perl and say, I can't believe that you treat a string as a number. But Rust, on the other hand, is almost the opposite. It's embarrassingly fussy. It distinguishes between the specific bit widths of different integer types. And so the difference between a 32-bit integer is just as different as, let's say, a string and an int in, let's say, a Python or anything else. In fact, it's worse than that. In Rust, you could have a data type which is defined as being 64 bits wide. So it has exactly the same representation as the native bit width of the CPU. So most programs we are running on 64-bit CPUs. So there's a data type which refers to an integer that is exactly 64 bits wide on every CPU architecture. And there's a data type which says, assume the size that the CPU architecture is the same. Assume the bit width of the native width of the CPU that you are being compiled for. Sorry, that's a very long couple of sentences to say that you could have two values that both have, let's say, the number 42 encoded as an unsigned integer with 64 bytes and this pointer width data type, which we called a U size. Every single bit is identical. All of the widths are identical. And yet the Rust compiler will refuse to allow them to cooperate. You couldn't add one with another. There is no implicit integer casting or integer promotion in the Rust language. And so Rust is very, very strict. And it makes things like error handling very frustrating for beginners because it's so pedantic.
And why does Rust handle errors the way it does?
Because essentially the language itself or the language ecosystem has said that if we push as much work to me, the compiler, if we can avoid problems, then we should. And if you have some cases where for example, I might compile my program on a 32-bit CPU. And so now the bit representation of my 64-bit type and my 32-bit type are different. And so this might imply some different semantics. And so now the inputs to the program actually include the CPU and the operating system that the program is being compiled for. And Rust is attempting to reduce the possibility of error by enforcing as much as it can at compile time. Once we remove the possibility of errors from our program, and that unfortunately involves being fussy sometimes, then we have programs which run exceptionally fast as they could by writing native assembly or even, let's say, C code, without the possibility that it could explode in your face, essentially. Because we don't need error checking in so many places because there are guarantees which are provided by the language itself and are checked beforehand, before it's even run.
So I presume the Rust creators did it that way because they'll have had experience with C++ and other languages where at the first pass you'll have written your program to do what you're trying to do. But then on the second pass, you might be thinking about, oh, hold on, if this is running on a different architecture, then we need to cater for what you've just explained, An integer might be different, so we need to do some checks for that, and we need to do some checks for this. And the Rust creators push that all to compile time because they've just been caught out so many times. Do you have any insights as to the history there?
So I know a little bit about the history, but I am probably second or third hand. But let's go. The Rust programming language was a sort of essentially an experiment when in its very early stages, far before 1.0, was an experiment on running programs currently safely. And there was an actor model, so it looked much more like an Erlang or Go than what emerged. After the project was adopted by Mozilla for this experimental replacement for the Firefox web browser, it became infected as a terrible word. But all of a sudden, a large number of C++ developers swooped in on the project and sort of said, look, if you really care about this thing, it needs to go super quick, and we need to prevent a whole bunch of bugs that C++ does not. And one of the bugs that C++ allows, because of its C heritage, are subtle problems related to what is technically called integer promotion, or essentially implicit typecasting. And if you allow that in the language, then you will encounter situations at runtime when the assumptions that you have as the programmer and the assumptions that the runtime has are going to differ. And so you'll encounter bugs. The Rust designers at that point made a decision after essentially using the language to build this new browser engine that we should be quite strict on people, because the language itself will find a home in the ecosystem of programming languages as being as fast as native code, but completely memory safe. And part of being memory safe, or part of the kind of the philosophy of the language of providing speed and safety, is that we should provide a very low overhead mechanism to handle errors. So in some sense, the Rust way, or the Rust approach, is in opposition to the C++ model by a large number of programmers who essentially became exhausted with trying to find concurrency bugs, trying to find bugs with exceptions just popping out of nowhere, and other kind of irksome things that they had encountered along the way.
Okay, so thanks for that, Tim. So now that we have Rust in the community for some years, well, quite a few years, at least 10, and people have experience with the Rust approach, would the creators say it worked out, or have there been changes to the way things did since they started? Or
yeah, I think that there has been a general trend in the industry towards, I would say, a functional style. The other thing which I haven't mentioned is that Rust incorporates quite a few concepts from functional programming languages. And what we'll see shortly is that Rust uses a very functional style from actually the ML family of languages that include Haskell and OCaml for dealing with its error types or the error process itself. And I generally think that a lot of ideas from functional programming languages have been adopted or incorporated into more traditional programming languages, let's say a Java or a C# or C++, these languages which have typically been associated with either imperative or object-oriented styles used heavily in quote-unquote enterprise software.
yeah, I spent a lot of time last year with Elixir, and then as I started getting into Rust more this year, it felt pretty similar with a lot of stuff. I quite like that when you're talking about the functional side of things.
Yeah, Elixir is a fun programming language. I have quite a few, I'd say, months verging onto years of mothballed Erlang and Elixir experience.
That's a good lead into my next question. So as a polyglot multi-language programmer, which we both are, I would say, we have opinions about dealing with errors in those languages, i.e. not Rust, be it good or bad. If we were to step back and push aside that we love Rust, how would we classify the developer experience for handling errors in Rust? Not knowing the whys that we already know.
Yeah, I think that the developer experience hurts in two places. It's uncomfortable when you start. It's different, and it is slightly unclear how to structure your programs because you don't get the same thing as exception. You're kind of in this unfamiliar territory where it's difficult to think about the way that your program is structured and the way that you want to implement something that would be easy in Python, let's say, or easy in whatever programming language. You come into Rust and suddenly you can't do that. And specifically, I'm talking about handling exceptions. The other thing that's quite challenging is once you have written quite a lot of Rust and you're starting to write your own libraries, you need to start to learn how to compose different error types. Now, this sounds slightly absurd to people that are unfamiliar with what I'm talking about, but the very end, probably 15, 20 minutes of what we're going to be chatting about with this kind of the fourth level of error handling, essentially is a large number of third-party crates or sort of open source libraries have entered the ecosystem of Rust programmers to plaster over it. It's more than just gentle sandpapering. It's essentially rethinking how errors work. And so there have been several attempts essentially to create an ergonomic layer of error handling over the top. And the things that we started talking about beforehand about Rust being very pedantic and actually become exacerbated when you have upstream errors that come from different places. Just very generally, there is a different category. We might use the word class, except Rust doesn't have classes, but let's call it a class of errors that are generated from I/O, input-output, such as the file that we try to read from, we don't have permissions to read from, or the file may not exist. That's a different kind of class of error sourced from a different module than an error that is related to parsing numbers in strings or formatting output, essentially converting data to strings. And so once you start trying to knit all of these different errors together, that's a place where Rust feels very clumsy. It's very bureaucratic.
My next question, are there any best practices for error handling?
I think the best practice is to work incrementally and kind of expand your knowledge. And rather than jumping to an ideal state, to stick within your mental model and then expand it as you learn more about the language. For example, Rust's trait system, a trait is sort of like an interface or an abstract base class. So we might say something is an error, which we could say it implements the error trait, is actually subtly different than what you might expect. And so if you try to go directly to an idealized best practice without developing a mental model, you'll probably end up becoming lost and frustrated. And so that's that is a hopefully that isn't me just kicking the question away. Another way to answer your question much more quickly is to say that the four levels that we're touching upon are a progression, and that eventually you'll end up at the fourth level.
Yeah, that's how I understood it. That's perfect. Okay, so briefly, Tim, what are the four levels in relation to the best practices that we've just spoken about?
Yeah, I mean, if we were to think about this is kind of we're progressing towards some idealized state, which I said is the nice way to do it. we could start essentially by ignoring errors and just crashing the program. That way, then we move on to using essentially untyped information and essentially providing a very, very basic something that feels like try catch with a very generic catch-all error. And then we can add some specificity. And the Rust way that we do this is by typically through creating an enum. Enums in Rust are a little bit special. They are richer than named constants. And then the last level is to essentially, I said plaster over some of the warts or some of the rough surfaces that the language exposes. The problem with using an enum, this level 3, is that we need to implement every trait or every interface or every combination of error that we might encounter. We also need to teach Rust how to print the thing to the screen, and that's quite clumsy. And so the latter level is essentially an extension of the third with simplified ergonomics.
Yeah, I think I made a mistake personally and gone straight for, I should be using this library and not fully understanding what I'm doing with it. The only thing I know is which crate to use if you're doing a library and which crate to use if you're doing a binary for users. But we'll get to that. So let's start with ignoring result of T, a result type. Type of result?
Yeah, it's tricky, right? So in source code, so we've got capital R result, and then angle brackets, capital T, close bracket. And that T represents the type that the result contains when some operation is successful. But it's frustrating because the initial T feels like it should be type, but actually it is a type, but it isn't directly clear what that actually means. So apologies. So yeah, it's not you, it's the language, or at least it's the convention. So blame the standard library authors for that.
So what do you mean by ignoring this? I mean, what would it, if you're using it, what would it look like and what are you ignoring here?
A result is kind of a meta type, where it's a type that has two sides. One is an OK side, which contains this T that we've been talking about, or it has an error side. And we could think of a result, which is just a wrapper type. It essentially is a container for something. And we hope it's the T, but it might be the E. And so we call a method on our result object, and I'm using the term object just to mean value. We call unwrap. And this essentially opens the result up, pluck out what we hope is the T. And we need to remember that Rust's type system is extremely pedantic. And so we say we expect that the value inside the result will be T. And then I can assign my capital T some value of type T to a variable. And if I'm wrong in that assumption, then I crash. That is one way to do it. Another is that there are some methods which take in a reference to something else. Let me have an example. Let's say I'm writing to a file. No, we'll go over the other way around. We're going to read from a file. So I start by initializing a buffer. And I have a buffer variable and a file variable. When I call read on file, I pass in a reference to the buffer, and then the method will return a result. If the result is okay, it's likely to tell me the number of bytes that was actually able to be read. And on the error side, we'll have some specific error message about the category of error. So for example, if I didn't have read permissions on the file, essentially the buffer will remain empty And one way to handle the error is just to essentially just go ahead and hope that your buffer has been filled up, and just essentially silence the program by assigning the result that is returned from the read call to a variable which is never read again. In Rust, errors are values. They do not interfere with the rest of the program. They are not like exceptions that will interrupt and break the flow. And so one way to deal with errors is, assign them to variables which are never used again. And we can be very explicit with the Rust compiler, which will be very keen to give us a warning to say that it's an unused variable by prefixing the variable name with an underscore to say that we essentially are discarding this value.
Okay, I'll summarize that if I understood it correctly. So the result is something that a function that either we write or we use from the standard library or another library is returned. So it's not the result of the function. The result is a thing, like you said. Think of it like an object. Inside that, it could have happy path, the OK, or the other path, which is an error. So we're expected to act on that result because that's why it's been designed the way it is. But if we choose for the simple way to handle errors, we just ignore it by assigning it to a variable that we don't use, and we prefix that with an underscore so the compiler shuts up.
That's right. Yeah. The difference between those two approaches, the one was to call unwrap on result, and the other was to use a variable which we never read from again, is that if you call unwrap and you're wrong and there really was an error, your program will crash. So they are subtly different approaches. Whereas if you assign a result object, which is an error, to a variable which is never used, then your program will proceed as if there was nothing wrong at all.
And we would potentially reach for this technique if we're just prototyping something or writing something quickly for ourselves. We don't want it to be bomb-proof.
Precisely. We would use an approach like that if there was, I guess it's two ways to think about it. One, you're just writing something that's 12 lines long. And the other would be that there genuinely is a situation where you don't care if an error occurred because the result, either side is fine, let's say. Essentially, I don't know when that would be the case, but presumably, it's available to you, but in practice, this is essentially just us getting started with the idea that a result could be either this happy path or this exceptional case, the error side or error side.
Okay, so that's level 1. Level 2 would be what we're calling, or what you've called, returning strings as errors. What does that look like?
Okay, so when we start to, let's decide to define a result. And we are not exactly sure what the caller or people that will be accepting our result as the return value of would want. We're still designing our API. One thing that we can do is to just push a string in there, and then if we want to essentially quote unquote raise an exception, all we need to do is put any text we want that's appropriate for the moment inside the variant of result. Then what our callers will need to do is interpret the text on the calling side. So, for example, let's talk about that case of reading from a file. You could imagine a case in which the read method on a file returns an error, or it returns a result which contains an error that is just a string. And then your question is, well, what was wrong? And so you go and look in the string and say, well, and we do our string operations. Does it start with permission denied? Well, okay, if it contains that substring, then we assume that the error from the operating system was permission, there was some sort of permissions error.
Perfect. So if we're looking into the string as an error, we would be returning that type of error to a user. So it's probably like a command line thing or something we would be writing.
Oh, so user in that sense is subtly different. This is the application code that is importing your library. So the user is not the end user, but some other programmer, some other code, which is probably code that you've written. So if you are defining a result type, which is quite easy to do, then it works in conjunction with methods on types that someone later on is going to be calling. And so the result that you are defining now will be interpreted by some other code that you probably don't have control over, especially if you're writing an open source code or you're releasing the library to the world.
Given your example there where you're interpreting the string for the error, and trying to understand it, you'd be at a point where you're trying to look for something else. Say, right, oh yeah, I understand it's permission denied, but what's the actual error number that I could look up or understand? Because you've got different levels for out of memory or can't write the file system or wrong user group, that type of stuff.
Right, and we can actually instead of returning a string, it's the same concept. We could return an integer. In fact, we could actually return, because we're talking about file I/O, we could return the libc error codes themselves that are defined by the operating system. Now, the interesting thing there with what you've just said is that you kind of need to look up the docs to figure out what the specific number means. Essentially, the code is not self-documenting. Or another way of looking at that is that it's open to a different class of errors. If you made a mistake, if you parsed an error message as a string or as an integer, but kind of misread something or you had a typo, and suddenly you've made a decision based on a misinterpretation of the code that is being provided upstream, you open the door for another error, which is the error of handling your one. Now, that's a motivating factor into kind of the next step. Is that clear?
Yeah, so we're at level 2, returning strings as errors. So we've gone past the step of just ignoring things. We're feeling a bit braver, a bit cleverer. We thought, oh yeah, let's put some meaning into that error. And then we've hit the next level where, actually we need to encapsulate some other type of information in that error. Then leads us to level 3, which is enums, I think. Is that right?
Yes. And the reason why enums work in Rust is because enums have two properties. One is that they are these named constants that you've kind of known from every language, where essentially instead of having a raw numeric code, we could give it a name. And we could group all of those error codes into some category, or, let's not use the word, but maybe a class. Now, though, that's kind of one type of enum. And Rust provides some sort of extra richness to this by actually allowing you to pack data into each of these variants. And so if you have ever used C has the idea of a tagged union, whereby one byte is used as a numeric tag, and then there's a sort of a struct, or you can push whatever you want into the remaining data. It could be essentially a type that is any type inside the same sort of packet. Now, in Rust, you also have one extra very nice property of enums. Because the compiler knows that there are, let's say, 9 different error types in our enum that we're defining, and you only handle 6 in your code, it will refuse to compile until you have added handling for the other 3. And allow me to say that again. Rust will require that you handle all possible cases and will enforce this at compile time. And so your programs that use, let's say, an IO error type, they will require that you have thought about essentially every class of errors that could occur. And this is, in some sense, much more powerful than just passing around an integer, because the compiler doesn't give you a lot of support. Like the C compiler doesn't really care if you've dealt with the integer correctly. Whereas in Rust, we can actually ensure that you have handled the specific error variant in the way that essentially was intended, because you have no need to parse any strings. The compiler can guarantee that you have at least thought about the cases that you're likely to encounter. You can have a catch-all pattern match, which essentially says that I don't care, but you've opted into that behavior, which is essentially a stronger thought than the compiler saying, I expect that you don't mind.
If we just go back to returning strings as errors, when we're returning something from a function, we have to act on that or assign it to a variable and ignore it. So if we're trying to pull apart, like you mentioned, you return a resultant and then you pattern match on it to act on it and check that things are as you expected. We can get in a mess if we're trying to match on strings. That's how I would understand that. But with enums, we can define what we want in that enum to mean what we want, and then Rust will complain that when that enum is returned from the function we've called.
Yeah, exactly correct. That, let's say that we, keep talking about the same error type, also the same scenario, but again, we're reading from a file. We might have permission denied. We might run out of memory. There's a lot of different things that could go wrong. The file could have been deleted. We don't want to have to interpret anything wherein the operating system itself can kind of do, like, it's giving us the information, and what the compiler does with the type system is require that you are lifted out of the problem of needing to interpret what it is that the operating system has intended. It's completely unambiguous. And it sort of is this very liberating feeling where instead of matching on strings or kind of, does it start with this, or, we often code in, let's say, TypeScript or JavaScript or Python or anything else. Or I sometimes say, like, any reasonable programming language, you just compare against string. Is it equal to permission denied or what have you? And Rust can provide something that is significantly more robust.
Yeah, so I was thinking in my head, going back to your C example, normally you'd do a match on if it's error code 1 or 2 or 9, or if it's an even one, it's okay. If it's odd, it's this. If it's negative, it's bad. So you have to think about all that and capture all that. Whereas that's forced on you with Rust if you don't just do an unwrap, i.e. level 1, and ignore the result. If you're doing a match on that because you want to be robust, you pull apart that enum and act on every level of it, or decide, like you said, and opt in to ignore 3 of the 9 possibilities you've created. Is that correct?
Yeah, that's right. There is another thing that you've snuck in there, which I am quite keen to chat about, which is that in many languages, and I was a Go developer for about a year and a half at one stage, and people used to return negative numbers to indicate that there was an error. And the other thing that they might do, especially in Go, is use the 0 value to indicate that there is a missing, like essentially an uninitialized value. So, for example, the empty string is essentially the same thing as saying no string at all. And Rust way to do that is essentially to wrap the integer that you are dealing with in another type and push a lot of work to the compiler and into the type system. Because if you forget to check, the negative numbers mean errors, then you have a real problem later on in your program because the thing is numerically valid and your problems will only emerge when some crash will occur because something occurred that was not expecting a negative number. And now you have to trace back, well, where on earth did this negative number appear? Like, oh, well, by the way, there was actually something. I should have dealt with that error when it was first created. And Rust is not permissive in that way. And I think this is a huge benefit to robustness in software.
When do you reach for the enum method, i.e. level 3 versus string?
Yeah, so I think if you're a proficient Rust programmer, very quickly. If you are just learning, or if you're still designing your library, you want to give yourself enough flexibility to be able to change things quite quickly. And so you're spending more time generating errors than handling them. And so the string method, or kind of this loosely typed or stringly typed kind of error type, is fine. But I would generally recommend that most programs that expect to live more than 2 hours should have a custom error type defined for them.
I like it. Okay, so I'm going to move us on to the 4th level. I think we've covered what an enum is well and how they help because they force us to deal with things, which can get in the way, but that's a good thing when we get to that level. Is there anything else you wanted to cover off in enums? Because they are pretty core to everything before we move on to the library section.
Yeah, maybe a motivation of why you would go further. And so one of the things that you could do with this is use the upstream error as one of the variants in your own error type. And so essentially you're creating a super error that combines or essentially allows you to compose other error types together. And this has 2 problems. One, it's actually a lot of work to define. It's kind of cumbersome in the source code. And then you have a lot of fairly mechanical work to be able to describe, essentially provide a representation of an error type as a string. And one of the things that we haven't talked about is that the error trait in Rust, that is the error interface, is primarily concerned with the ability to serialize the data type itself. That is, all errors should be able to be printed to a log file, and which is one of the reasons why string is able to be used as an error type. And in the case of an enum, a new type that you define, a custom user-defined data type, has nothing implemented at all. You start by when you grow a type, essentially when you define it, you also need to define every single interface that it implements, or every single trait that the type actually works with. That includes how to print the thing to the screen and to serialize it. as a stream of writes.
Thank you. So you're now elite. You know what you're doing with all the errors. You've hit level 4. And then you realize, oh, I don't need to do this anymore. I can just reach for one of these libraries. Or I can completely rethink how I do it because somebody else has created this library. Is that how we've got to level 4?
Yeah, that's exactly right. So you've just gone and listened to nearly an hour of me saying, oh, you've got to do all this heavy work. And now I'm going to tell you that, by the way, most of the work has actually been dealt with. And the process of defining your own error types is quite simple these days with the help of macros, essentially, which do the job of telling the compiler what to do so that you don't need to write it in source code. And I hate being one of these people that does the same thing, which I remember really disliking, which is essentially teaching all of the fundamentals before teaching this advanced cheat. However, I feel like in the case of something as fundamental as error handling, it really does help to understand what these libraries are doing. Otherwise, you mishandle them, or otherwise it becomes magical, and I am strongly opposed to magic in software.
Yeah, it's the same as any computer book. You need to know the fundamentals before you can use the abstractions, I think. I agree. So in your talk, you've got 3 main ones. First one is called this error with no spaces. Second one is anyhow, or one word, and then error, the third one. We're getting close to the end of the show, so if we could spend a couple of minutes on each 3 and where you would use them, then I'll move us into starting to wrap up.
Yeah, no, please, that's absolutely fine. This error is a library for defining an enum which represents different variants. And so, for example, you'll say that it has little helper macros for saying, this is the string that I want to print out if this variant is encountered. Or I am wrapping an upstream error, and so the thing that I want the compiler to do is to dispatch to the upstream error, for example.
And would you be able to change the upstream error to something that means something?
Yeah. You can essentially, it provides you with a couple of hooks to be able to simplify things or to make them more specific. So, for example, actually, if you look at the documentation, in the front page, there's an example, which is a data store error. So we are writing a library that is a client library for some sort of database. And one of the types of errors that our enum has is a disconnect. So the data store, the underlying network socket has shut down. The library that we're writing, we don't know why that shut down. And so we actually essentially inherit from the standard library's own error type. Inheritance, though, is a very muddled word in that case, but essentially we wrap the standard library's own IO error, and then we provide our own context, which is data store disconnected. And then essentially it then prints out the secondary, the inner error.
Yeah, I was thinking of something like where you're using a third-party JSON API or something, and then you know that when it returns a 500, it's actually okay or something. You can trample over that error.
Oh, yeah, no, absolutely. That would be a perfect thing that you could do. You would, given the opportunity to go and inspect whatever has been received, it's like, oh, well, actually it's a 500, but let's say 500s in this instance are actually acceptable because they have the API does not respect the standard. So 500s actually are signals that there was an empty data set, for example.
And I understand this error to be used, well, for you to use it if you're speaking to users of your program. So there are error messages for command line user, something like that.
Yes, there's sort of this kind of strange debate about which library should be used for application code versus libraries, which is a distinction which I actually don't think is particularly helpful But actually, the latter two libraries that we're going to talk about now would probably, in most instances, be more appropriate for quote application code. This error crate is a way to define your own result type, which provides a lot of specificity, but it has the downside that your code it involves us a kind of bureaucratic approach where every single instance needs to be handled. And in application code, sometimes you don't care exactly why there was a problem. You just want to know that there was a problem and maybe annotate the output with some sort of context, or it's like, well, I was trying to do this. And that's the log line that is printed out. And for those kinds of use cases, the latter two libraries that we're going to be talking about are probably better suited.
Okay. And the next one would be anyhow.
Right. So I would like to actually chat about anyhow and Eyre, as in Jane Eyre, the E-Y-R-E spelling, as essentially being two subtly different versions of the same idea. And you should use whichever flavor of that idea you prefer. But they are conceptually identical. They're just different takes on the same idea.
Perfect. Okay, I think we better wrap up. So thank you. I'm really glad we did this and hope it helps others like me. Was there anything that we missed that you'd like to mention?
No, just the only thing would be if you're having trouble with Rust, to give yourself a breather and essentially allow your body and your brain to absorb the language piece by piece. It introduces a lot of semantics that are different than other languages, and Rust can feel very strict and in some cases pedantic. And I think that that's because it applies subtly different rules than what you're used to. And so it will take time for your brain to kind of adjust and be patient with yourself as you're learning.
Cool. Well, people can follow you on Twitter. Is there any other way you'd like them to get in touch? Or
yeah, look, if you're off Twitter or X, I'm also on Mastodon and also YouTube. I've increasingly am now making my content available on YouTube, and that's a very good way to follow me if you like worked examples, because about once every couple of weeks, I put on a live stream where we go through a small exercise and implement it. And I try and fumble my way through any compile errors that appear.
Yeah, I've watched some of those and joined them. They're really good. Thanks for doing those. Thanks for coming on the show. It's been a real pleasure. This is Gavin Henry for Software Engineering Radio. Thank you for listening.
Thanks for listening to SE Radio, an educational program brought to you by IEEE Software Magazine. For more about the podcast, including other episodes, visit our website at se-radio.net. To provide feedback, you can comment on each episode on the website or reach us on LinkedIn, Facebook, Twitter, or through our Slack channel at seradio.slack.com. You can also email us at team@se-radio.net. This and all other episodes of SE Radio is licensed under Creative Commons License 2.5. Thanks for listening.